Okay. We'll make it full screen.
Yeah.
Also, maybe just making this more.
Yeah.
Just move to the side.
Perfect. Yeah. Okay. And if I just speak normally, it's okay? Or...
Yeah. Now it's fine.
Okay.
So the voice is turned on. It's recording. Okay. Yeah.
If people on Zoom, you can hear.
Can people hear us on Zoom? We should be able to. Anyone on Zoom can answer me? Can you hear me?
Yeah, we can hear you.
Yep.
Okay.
Look at the names.
I guess maybe the relevant question is if I speak, can they hear me?
Yeah.
Yeah, that's cool.
It should be. I have the recording, so it should be able. Okay. So hello everyone, welcome to the primate seminar. Today we are pleasure to welcome Professor Zhou Fan to talk about the dynamical mean field analysis of adaptive Lagrange diffusions. Okay.
You're muted.
I'm muted.
That's why they.
No, there his computer is muted.
So my computer is muted.
This one is okay. Yeah.
We don't know.
Okay, I'm gonna start talking, and if
They see the mic.
Yeah. Okay. Great.
Yeah. Okay.
Yeah. Thank you for inviting me to speak here. I kind of regret not having interacted too much with the applied math group here at Yale over the past few years, but it's nice to see some new faces. Also, I see a lot of students from our department here, so thank you. So yeah, this talk will be about some work that we've been doing over the past couple years on analyzing what I'm going to call adaptive Langevin diffusions. This is yep. This is joint work with a few fantastic collaborators, Justin Coe, who's at the University of Waterloo, Bruno Luero, who's at ANS Paris, Yue Lu at Harvard.
Yes. The screen share is paused.
What does that mean?
Try to reshare it.
Oh, I see.
Yeah.
Does this work now? Okay.
Yeah.
Yue Lu at Harvard and Yandy Shen, who was a postdoc working with me here, and he's now at CMU. Okay, so the topic of my talk, the particular model and process that I want to talk about today is going to be something that's very specific, but I at least want to try to motivate this topic by giving a slightly broader or more general kind of one slide introduction, which is that this talk will be about learning on one hand and sampling on the other hand, and in particular about trying to do some learning via drawing samples. So it's going to be a talk about trying to do parameter estimation by sampling from some distribution. This kind of paradigm is quite common in statistical learning. A classical example of this kind of paradigm is, for example, going back to the work of Hinton in 2002, contrastive divergence methods for maximum likelihood estimation. These are problems where you have some likelihood function that is intractable. So there's some normalizing constant of the likelihood function that's intractable. And in order to try to learn some parameters to maximize its likelihood, we try to draw samples from the distribution that's represented by current parameters in order to approximate the gradient of this likelihood function and take a step in the gradient direction. Even older than this are ideas in latent variable models. So it's a kind of similar setup where we might want to learn parameters of a model where you have a lot of latent variables. And because you have a high dimensional latent variable, the form of the likelihood is also intractable in these examples. One common kind of approach to learning these settings is to use something like an EM algorithm. And frequently in EM, when we try to do some E-step computation in EM that requires computing an expectation over some high dimensional distribution that might still be intractable. And so Monte Carlo approaches to solving the CM problem have been proposed, where I try to do Monte Carlo sampling of these latent variables in order to approximate the step. So this is the second example, and the subject of my talk today will be in the flavor of the second example. And then more recently, I guess there's been interest in these kinds of sampling-based approaches to learning in the training of diffusion models. In particular, one kind of context in which this arises is for fine-tuning of these models. So this is a setting where you have a distribution of data that's perhaps implicitly represented by the score function of the distribution, so the gradient of the log density. And then what you want to do is maybe to optimize the parameters of the score function to optimize some objective about the distribution that this represents. So for example, if it's a distribution for images, you might want to tune, I don't know, like the color or the opacity of these images. And because you don't have direct access to this distribution, one approach that's been suggested is you run some kind of a sampler to draw samples from the distribution, for example, a Langevin dynamics kind of procedure. And then after you draw samples from this distribution, you try to optimize this objective over the samples. So these are all examples of this paradigm. And there are some things that are in common about these kinds of applications or these settings. So in all of these settings, we're trying to do some parameter learning. And the parameter that we're trying to learn, I'm just going to call alpha throughout this talk. Alpha is some two-dimensional parameter. These applications all have a common characteristic that the space in which we're sampling from is typically high dimensional. The reason being that these problems are intractable because the space is high dimensional and there's some high dimensional integral that we can't attractively compute, and so we're resorting to sampling to approximate this integral. And then the other thing that these examples have in common is that they're all iterative. So what I mean by this is that all of these methods, they're doing some learning, and then they're using the learned parameters to draw some samples, and then from these samples, they want to do some more learning to update the parameters, and then you want to use the updated parameters to draw some more samples. And so because of this iterative nature of these procedures, I think it's very natural to start thinking about Monte Carlo sampling methods where instead of iterating back and forth between these steps, you're simultaneously evolving both of these steps, right? So you're running some Markov chain Monte Carlo sampler where the target distribution that you're sampling from is continuously evolving or adapting to the samples that you've already seen. And so this is what I in general mean by an adaptive sampling or adaptive Langevin procedure. And so very broadly, the subject of my talk today is I want to do an analysis of one procedure of this form. And we're interested in questions like what are the fixed points of these kinds of processes and how can we try to understand these things. Okay, so let me get into the specific model that we're talking about. So the setting of the talk will be a particular example of this kind of a procedure. I think it's a particularly simple example in this context. Where we have a linear regression model. So I have some high dimensional regression design X, and I observe linear observations Y. And it's a latent variable model in that the regression coefficients, I'm calling here theta star, we're assuming that they're latent random effects. So they're coming from some distribution. This distribution, if you think about a Bayesian setting, you can think about it as the prior distribution of these effects. And we don't know this distribution. So there's some parameter, I'm calling it again alpha, that parameterizes this distribution, and I don't know what this parameter is. And I want to try to learn what this parameter is from the data. So in statistics, we would call this an empirical Bayes kind of setting where I have this Bayesian prior and I want to learn this prior directly from the data. And I should say that this particular empirical Bayes problem arises pretty ubiquitously in genetic association analyses. And at least the starting point of how we got into this problem back a few years ago was we were motivated by these kinds of methods. There's a large suite of software packages that do genetic association analyses using these kinds of random effects or Bayesian linear models, where under the hood, each of these software packages is implementing some version of this learning. Right? They want to learn the distribution of these effects, which in a genetic context would be something like the distribution of genetic effects for some traits across the genome. So we want to understand how sparse are these effects across the genome, how much of the variance is explained by the top 10% of the effects, et cetera. And so
without interactions.
Okay, yeah, you can make the model more complicated for sure, but here this is without interactions, just assuming some ID effects. That's a baseline. Okay. So I think thinking about this problem statistically, the sort of natural or the approach that I think all of us would think about and try to implement is some maximum likelihood procedure. So I want to estimate alpha by maximizing the likelihood. In this case, it would be the marginal likelihood. I need to marginalize over all of these random effects theta star. And if you think about this from a statistical perspective purely, there were a couple recent papers, one by Mukherjee, Shen, and Shen, and one by our group here at Yale, that established that, okay, under some pretty general conditions for this problem, if the dimension and the sample size are both going to infinity, this estimate would be consistent for estimating what this prior parameter is. But the kind of issue that arises computationally is that this marginal log likelihood in this model is intractable. Its gradient is also intractable. Right? So if I call the marginal log likelihood log, so this P of y given x is just the marginal probability of y integrating out theta star in epsilon. And this alpha denotes that we're considering the prior with parameter alpha. Then computation of this would require computing this integration over theta star. And if you do a calculation of what the gradient of this should look like in the alpha parameter, it's not too hard to check that the form of the gradient, it takes the form of a posterior expectation. So I want to compute an expectation over a posterior sample of theta, given my data x and y under this prior, of the gradient of the log prior density, evaluated at the coordinates of the posterior. And then this is a few lines of algebra, you can check this. And the issue is that, to exactly compute this posterior expectation, again, might be intractable. Okay, good. So the setting of my talk today is then the following. So we can try to come up with sampling-based approaches to try to approximate this computation. And I'm going to focus on a particular sampling method that we suggested or proposed in a paper back a couple of years ago. This is with Le Yingguan, Yan Di, and Yihong Wu. I'm going to refer to this method as an empirical Bayes Langevin dynamics. Actually, I recognize that I think back maybe a year ago, you guys very kindly invited Yandy to come give a talk at the seminar also. And I think Yandy spoke about this work or this earlier paper of ours. So let me just review a little bit what this method is doing. So it's doing two things at once. The first equation that you see there is just a very classical Langevin dynamics sampler for sampling from the posterior distribution. Right? So this is a diffusion in this d-dimensional space for theta. Theta is the regression coefficients. That's driven by the posterior law. And the posterior law has a parameter, and the parameter here I'm calling alpha hat t. So this is a parameter that's at the same time as we're running this Langevin is evolving forward. So coupled to the sampling equation is an evolution equation for the parameter, where I want to do a time evolution of the parameter. And the time evolution of the parameter is going to try to implement some kind of gradient descent or gradient flow procedure for maximizing this marginal log likelihood. So if you recall, this was the sort of the form of the gradient of the log likelihood was exactly this expression where I want to compute the expectation over a posterior sample. And because I don't know how to compute this expectation, what we're proposing is that you run this Langevin sampler and then given the sample that you see, sorry, this should be theta t with a superscript at time t, you approximate this calculation by computing this on the coordinates of your drawn sample. Okay. And an important observation maybe is that whatever this object is, it's some functional of the empirical distribution of coordinates of my current sample theta t. And I'm just going to start using this notation p hat of a vector to denote the empirical law coordinates of that. Okay. So to summarize, this is a process where we're simultaneously, so going back to my very first slide, we're simultaneously running a sampling procedure to sample from the posterior distribution of theta, as well as evolving a learning process that's learning this parameter alpha based on the samples that we see. Yes.
If the thetas were from the true posterior they're supposed to be from,
yeah,
that alpha derivative would be like an empirical estimate of the actual gradient of the alpha marginal.
Yes, that's correct.
So if the thetas were from the right distribution, this
exactly
would be Langevin diffusion for alpha, or approximate Langevin.
Well, it would just approximate a gradient descent for alpha.
Yeah, okay.
Right? So if theta is actually drawn from the posterior, that's great. Then this is exactly approximating what the gradient step should be for the log likelihood. But the point is, I'm not sampling exactly from the posterior. So we expect that, we hope that maybe this chain of dynamics will eventually converge to something close to the posterior. And at the same time, I'm just simultaneously evolving. So That's exactly the right intuition. Okay, good. And so I think that probably if Yandy gave a talk about this back last year, so there is a purely optimization-based interpretation of this procedure as some kind of a Wasserstein gradient flow for the Gibbs variational form of the log likelihood. I'm not going to get into this interpretation today. It's not so relevant for what I want to talk about. So we can do this. And so there's also been similar kinds of proposals of algorithms of this form recently in the literature from some other groups, due to Kunz et al. And Kildietze. Okay, and so the kind of theory that has been understood for this procedure is of the following type. So in our first paper on this, we analyzed an idealized version of these dynamics, where instead of driving alpha by the coordinates of my sample, I suppose that alpha is actually driven by the true deterministic law of theta t. We made this approximation without really justifying it. And then in these works in recent years by other groups, it's also understood that, for example, if you run these dynamics in a way where instead of having one Langevin sampling chain, you have many, many parallel chains all going together in theta. And then when you're driving the gradient equation for alpha, you're averaging not only over the coordinates of a single chain, but over all of these chains. Then that's a sort of much more classical setting of like a Mikhine-Vlasov kind of process. And there's sort of standard propagation of chaos kind of results that show that you would get a consistent estimate of alpha. But so the kinds of, okay, so I want to address the following two questions in this talk. The first is that, so in the applications that we care about when we have these high dimensional models, this dimension D itself of this chain might already be extremely large. It might be tens of thousands, hundreds of thousands. And I can't really run many, many parallel chains to try to do the sampling process. Ideally, I just want to run a single chain. And the first question I want to ask is something that I'm going to call a single chain propagation chaos result. So if I only just have a single Langevin chain from this dynamics, and I just do the dynamics in this way, is it true that this alpha hat parameter will converge? Limit, is it true that the laws of theta t will converge to some deterministic limit? And the hope is that this might happen if the dimension of the single chain is going to infinity and there's enough self-averaging over only the single chain. So this is the first question. And then the second, I think perhaps even more interesting question is that can we understand the fixed points of this process, right? So if theta t were really being sampled from the posterior, I would expect this to approximate some gradient optimization log likelihood. But here we have a simultaneous evolution of the law of theta t together with this alpha. And so at the end of the day, what can this converge to? If there's a true prior parameter alpha star, does this actually always converge to alpha star? Can it converge to some other kind of fixed point? And we characterize what these fixed points might look like. And so this is the second kind of question to address in this talk. The second question in particular feels quite hard to address in a general setting. And so the subject of my talk today is that we want to give answers to these questions restricted to maybe a toy setting where the random design is not ideal. So I'm going to consider in this regression problem my design matrix to be IID random. And before getting into these questions, let me just show maybe a quick video of this method, and then perhaps Yandy, if you talk to me to show this video. This is just an illustration of what the method is doing. What you see on the right, so the black curve is the true prior distribution in 4 different simulation settings from which I'm drawing these regression coefficients. What you're seeing in the left panels are the histogram of coordinates of this Langevin sample, and it's running over time. So I do this Langevin sample, and we're evolving the histogram of coordinates over time. And then what you're seeing on the right in the red curve is the learned prior density represented by this alpha, and it's running over time. So actually, in this illustration here, we're being pretty non-parametric about how we model this prior. So this actual alpha parameter is something like 60 or 100 weights over this interval. The kinds of applications that I'll discuss later in my talk today will be much simpler applications where alpha has maybe just 2 or 3 or 4 parameters, so we can focus on these lower dimensions. Okay, let me pause to see if questions. Okay, and yeah, please do, if you have questions, please do just. Okay, so the outline of the rest of the talk is the following, and I think it might be a somewhat ambitious outline, but we'll see. I want to present 4 results on this. The first will be about this first question of single chain propagation chaos. And then the remaining results are all oriented towards understanding the fixed points of this dynamics, what this converges to. Okay, so the first result I want to explain is this. So first of all, the setting that I'll assume throughout the talk, let me just make it clear here. We're going to consider an asymptotic setting where the sample size and dimension are going to infinity proportionally. They're converging to some constant delta. My regression design X, I'm assuming, is a random design. So it has independent entries, mean 0, and scale in a certain way, variance 1 over d. The true response vector Y is a linear model where the regression coefficients, the true regression coefficients theta star, they have IID entries from some prior distribution that I'm calling G star. And then we're trying to learn or model this prior distribution using some parametric family. So I have a family of parameterized priors parameterized by some alpha parameter. It's not really important whether this parameter, this family actually contains G star. So you can think about the case where G star is in this family, but you don't have to think about G star as some arbitrary thing we're trying to learn. And then our assumption for the prior is that they don't have to be log concave, but we're assuming that they're log concave at infinity. So what this means is that outside of some bounded interval, the tails of the prior are concave, and then within this bounded interval, they can kind of have. And then for the initialization of the dynamics, alpha, this parameter, I initialize just at some arbitrary deterministic value, let's say. And then the coordinates of the Langevin process, I'm initializing for simplicity, just IID, some distribution. Okay. So this is the setup. And the first result I want to explain in the setup is that, so it gives an answer to this propagation chaos kind of statement, that indeed there does exist a deterministic continuous process alpha over time. This is a process in RK. As well as deterministic laws. So there are stochastic processes with deterministic laws that I'm calling theta and beta, such that if I look over a fixed time horizon in the limit of increasing dimensions, my learned, so the trajectory of my learned prior parameter alpha t will converge in the sense of uniform convergence to this deterministic path alpha. And then the empirical distribution of coordinates of theta star together with the sample paths of my Langevin trajectory will converge in a Wasserstein sense to the law of this univariate process. And if I care about the prediction error or something like this on the side of x theta rather than theta, the empirical distribution of coordinates of x theta star together with the sample paths of x theta will likewise converge in a Wasserstein sense to a deterministic way. So this is the first result. I haven't yet told you what are the forms of these laws, and I'll show you in a couple of slides what these are. Okay, so this result, where it comes from is we use techniques of a field that's called dynamical mean field theory. And let me first try to explain at a high level just what this is if you've never seen it before. It's a method of approximating the dynamics of like an interacting particle system where I have random interactions. So if I have d interacting particles, and you should think about these as the d coordinates of this vector theta that we're evolving. So I have these d particles, and they have random pairwise interactions. Then the sort of high-level idea of dynamical mean field theory is that we want to approximate the interaction between any particular coordinate, let's say the jth coordinate theta j, and all of the other d-1 coordinates by an effective mean field. So I want to approximate this interaction by some kind of a scalar Gaussian field. And after making this approximation, this will give me an effective just univariate dynamics for this one coordinate theta j. Now, the statistical properties of this mean field are going to depend on the distribution of this theta j. So if I then look over these univariate dynamics for all of my coordinates, the average behavior of all these coordinates is going to determine what should be the statistical property of this mean field. And this whole body of theory, so because of this, has a kind of fixed point nature, where I have some mean field whose statistics are determined by these trajectories of theta, and then the trajectories of theta themselves are driven by this interaction.
Do you have any assumption about the potential of the interaction?
Yeah, so I'm being extremely vague here, but so this is under an assumption that you have random pairwise interactions between theta and some other, between each theta and each other theta. So the simplest model might be something like the potential is like theta transpose some IID Gaussian matrix times theta.
Do they have a decay or some kind of
so it doesn't even have to be a potential. There doesn't have to be an underlying potential. It can just be some dynamic system process. We're making approximations over finite time horizons, so the process can explode as you get as time increases. Right? So it doesn't even have to have a potential. But what's important is the sort of pairwise interaction. So the evolution equation of theta is going to depend on the other thetas, and this dependence is determined by some random variables, which in our regression setting are coming from this random design. Okay. Right, so this kind of technique was developed in statistical physics. It was first developed by Sampolinsky and Zepelius for variants of the SK model, and then by Crisanti et al. And Cugliandolo and Perkin for spherical versions of this model. Over the years, there have been a few different mathematical formalizations of these results. The earliest ones were due to pioneering work of Benarus and Guillaume in the 90s. Where they studied these kinds of dynamics for Langevin type for SK type models, and were able to prove mathematical statements about this kind of DMFT using a large deviations approach. And then our work and the methods that we use to prove the theorem I just mentioned a slide ago is largely motivated by a more recent result by Salentano, Cheng, and Montanari back 4 years ago, where they recognize that actually you can prove this kind of result that I'm about to describe by reducing this algorithm to something called an approximate message passing procedure. That you can discretize this process in time, map it to some approximate message passing procedure, and use some existing theory of AMP to then deduce the equations that I'll show you on the next slide for processes. And so the approach of our analysis for this theorem is very close to the kinds of analyses that were done by Salentano. Okay, so let me explain what exactly is the description of this limit. And so as I mentioned a moment ago, this description is going to have this kind of fixed point nature. So I give you some sample path alpha t, which is supposed to represent the deterministic limit of this prior trajectory. And I also give you two kernels, a correlation kernel and a response kernel. And then there is a description of the univariate dynamics of theta that's given by this kind of a diffusion equation. Okay, and so in this equation, you should think about theta t as just representing one particle of the system, particular coordinate theta j. This first term here is essentially exactly in the high dimensional dynamics. What is the dependence of the drift for theta j in terms of itself? So the direct dependence on theta j itself is this. It's just reproduced in these terms. There is a univariate Brownian motion that you should think about as that coordinate of the high dimensional Brownian motion that's driving the Langevin dynamics. And then the part where theta j depends on all of the other coordinates is the part that we've replaced in blue. So this is the effect of this mean field. So there is a Gaussian variable ut that you should think about as the mean field. And in the asymptotic limit, this distribution of the mean field will be Gaussian. So it's some Gaussian field or Gaussian process. And then in the kinds of dynamics that we're looking at, so this one particle is going to interact with this mean field. And then at a later time, this mean field is going to interact back with this particle. And because the randomness of this forward interaction in our model is the same as the randomness as this later backwards interaction, that sort of backwards effect does not cancel. You can't neglect it in large system limit. And what this leads to is a direct dependence of theta t, the dynamics of theta time t, in terms of the past history of this particle itself. And this dependence takes the form of an integrated linear response, where you have a response kernel also. And then the characteristics of this response kernel will be defined self-consistently also from the properties of these dynamics. And then on the other side of this, if I want to look at the dynamics of this thing that I call eta, that approximates not theta, but x theta, there's a very similar kind of description that if I give you two correlation and response kernels, this correlation kernel is going to describe the distribution of some mean field variable w. Then again, you can think about the dynamics of a single coordinate of x theta as approximated by this univariate dynamics, where there's this interaction with this mean field. And then to close the sort of fixed point equations, these objects, the alpha and then these two correlation kernels and these two response kernels are defined self-consistently by the laws of these processes. So I have these two processes, theta and eta, and from the laws of these processes, I look at their two-point correlation functions, and this defines the correlation kernels of the mean field. This alpha that's supposed to approximate the dynamics of my learned parameter is now evolving according to the same evolution equation, But instead of looking at the empirical distribution of coordinates of this high-dimensional long-term process, I'm literally just driving it by the law of this variable theta t. Right? So there's this deterministic evolution of alpha that's driven by this law. And then there is a description also of these response kernels in terms of some auxiliary processes that at least formally are defined by differentiating the previous evolution equations in the field variant, Gaussian field variables. Okay. And so the way you should understand this whole thing is that it is a fixed point system. What this describes is a dynamical fixed point system in these 5 variables, alpha and the 2 correlation kernels and the 2 response kernels. Given these things, we can define these stochastic processes previously, and then from the statistics of the stochastic processes, we come back and define these. And so the theorem, what it's saying is that there is a fixed point to the system. We can show that this fixed point is unique in a certain domain of functions having exponential growth. And this unique fixed point is representing the large system limit of this adaptive logical process.
Oh, sure.
Yes.
Could you go back a slide previously to see?
Yes.
Okay, thank you. Nice.
Okay, yeah. Okay, so this is this, I guess, propagation of chaos kind of.
So you said that the fixed point is unique, and earlier on you said like if theta and alpha were from their proper distributions, that would be invariant. Does that mean that that is the fixed point, or is that?
No, so okay, it's a good question. When I say fixed point, it's not a fixed point in the long time limit. I have these functions of time, and it's a fixed point. It's a system of fixed point equations in these functions of time, and there is a unique functional fixed point. So what this fixed point depends on, I have some initial condition that I initialize this algorithm from, and so the behavior of these functions depend on this initial condition, and there's sort of these kernels or functions of time, and then there's a functional fixed point. Right? It's not a fixed point. It's not supposed to be. Okay. So what I want to do for the rest of the talk is the following. So I think the whole one of the kinds of issues with this whole DMFT business, so this has been around for a while, and I think one of the kinds of issues with this is that the limiting process that's being described by these equations is not particularly simple. Maybe you can agree with me on this point. And so one of the challenges over the years has been the question of whether we can actually gain some insight or understanding from this limit. So there's been a lot of interest in these DMFT approximations, I think recently in machine learning and in statistics, and actually a lot of these recent papers, after arriving to this point of writing down this DMFT system, it's simulation-based. They write down some simulations that simulate these stochastic dynamics and solve this numerically, and then plot trajectories of what it looks like numerically. It's perhaps not entirely clear if simulating this fixed point is easier than simulating the original high-dimensional dynamics itself. And so there's always been this question of, can we gain some kind of analytic insight or some understanding of this process? And I want to spend some time for the rest of the talk trying to explain some efforts that we made to it. Yes.
Sorry, I was about to ask something to that.
Yeah, sure.
Is there an easiest case where you can solve this?
Yes, that's a good question. If your prior is Gaussian, and let's say it's fixed, you can solve these equations. Solving the equations is not trivial because but they're essentially these Volterra integral kind of equations, and you can do Laplace transforms, Laplace equation techniques because everything's linear, and you can explicitly solve for all of these equations. At some point, we went through this exercise. But outside of the linear case, I think it's hard to solve.
So that's also assuming the X is also Gaussian.
This is assuming X is Gaussian. This whole theory is assuming X is accurate.
Generally, when is it the case that you end up with this memory term?
You mean this integrated response kernel here? Yeah, so it's arising in these symmetric dynamics where, you can imagine, if you think about like in this case, if you think about a model where a simpler model, d theta t is just x times theta t, you'll get this kind of response kernel if x is symmetric. Because when x is symmetric, then your forward interaction of xj with the rest of the vector is captured by a particular row of this matrix. Your interaction from the field back to this is captured by a column of this matrix. And if you have a symmetric disorder, then that randomness is the same, and you'll get this kind of integrated response term. if you consider a variant of these dynamics where you have like an asymmetric, just IID Gaussian matrix, then my understanding is in these dynamics, you don't get this kind of integrated response.
It's like, why doesn't it show for the multiple chain propagation of gas?
What do you mean by multiple chain?
Now you can have multiple particles. The limit of those systems do not have this history dependent character.
Oh, because there's no random disordered interaction. There's no, when you look at a particular, in the standard propagation of chaos setting, when you have multiple particles, they're only interacting through the empirical measure, right? So we're looking at a model where in addition to this interaction through the empirical measure, there is a sort of pairwise interaction between each particle and every other particle that's described by this random disorder. And this is random disorder that's leading to these moments. Okay, good. So let me get into, right. So for the rest of the talk, I want to try to interpret a little bit these equations to try to make some sense of things that we can understand. So the first thing that I want to do is to give an interpretation of these correlation and response kernels that are arising at this DMFT fixed point. And the reason this is called a response kernel and the interpretation is related to this notion of a response function in these dynamics. So if I consider the kind of dynamics that I have, so I have some Langevin dynamics of theta, and if I want to couple it to this deterministic dynamics for alpha, the notion of response is that if I were to perturb the potential of the dynamics by some small amount, so epsilon is some small constant, I perturb it by some observable that I'm calling B of theta, and this perturbation is modulated over time for a second by this f of t. I consider the solution of this perturbed dynamics, and then the notion of a response function in physics, I guess, is that this response function, this response kernel, RTS, is a function such that if I want to then look at perhaps different observable A at some time t, and I look at the derivative of its expectation with respect to the size epsilon of this perturbation, that this derivative is given by the integration of this response against this f, this time observation. And perhaps the more intuitive way to understand this, and the way that I think a physicist would write this equation down, is to think about S as like is to think about F as a Dirac delta perturbation at a single fixed time. So if you think about, at some time S, I make a Dirac delta kind of perturbation in this direction of B, and then at a later time t, I measure what is the response of this observable A. What we're saying is that the time derivative in epsilon of that response is exactly RA BTS. This is, I think, how you should interpret this intuitively. But to make mathematical sense of this, we can, integrate this. You can, instead of doing a single time perturbation, you can modulate this perturbation over time by any function f, and you would get an integration with respect to f. And then usually in the discussion of the response function in this area of statistical physics, you would think about it in conjunction with the correlation function, which is just a two-point correlation function process. So for the same two observables A and B, you can define a correlation function, which is just literally the expectation of the value of A at time t and the value of B at time s. And then there's a celebrated and fundamental result in statistical physics, I guess, which is if you consider a non-adaptive version of Langevin dynamics for a second, so there's a fixed target measure, and you're at equilibrium, which means your process has already equilibrated to that target measure. Then first of all, these correlation response functions, they wouldn't depend on the times t and s individually, they would depend only on the time lag, so the time translation variant. And then there's a fundamental result called the fluctuation dissipation theorem that says that the response function is given by the time derivative of the correlation function. So in words, I can predict if I make an infinitesimal perturbation to the potential of the system, and I look at, what is the response of this perturbation, I can predict that response through just the two-point correlation function of the unperturbed system at equilibrium without an interaction. So it's this relation between this external perturbation and this two-point correlation. And in physics, this was developed, I think, in the 50s and 60s, or maybe going back even earlier to some earlier work. And then in terms of like a mathematical or probabilistic formalization of this, The earliest reference I'm aware of is by Dembo and Duchel in 2010, who gave a formal mathematical statement of what this means, and the statement is something like this. So I consider again a non-adaptive dynamics. Suppose there's a unique stationary distribution, I call that Q. I consider two observables A and B, and I define both this correlation function, this expectation, as well as the previous response function. I do it for a fixed initial condition. So if I fix your initial condition X, define these expectations, fixing this initial condition. Then first of all, what was shown by Dembo and Duchel is that there indeed exists a response function that satisfies this previous property I wrote. There's an explicit form for this response function, which I'm writing here in terms of the Markov semigroup of the process. It's the expectation of the gradient of B at XS times the gradient of the conditional expectation of A at time T. And then if I were to initialize this initial condition X itself from the stationary distribution, from the equilibrium measure, then I have this fluctuation dissipation relation, which is that the expected value or the average of this response is exactly the negative time derivative. Okay, so the second result that I want to explain is that if I go back to this DMFT system, this dynamical fixed point, there's an interpretation of these correlation response kernel objects that are appearing in this limit. It's an interpretation that I think is understood in the physics sense, but I haven't seen before formalized in the mathematical sense. And the interpretation is just the following. These correlation functions, if I look at C theta TS, they just represent, if I look at a single coordinate observable, I look at the jth coordinate of theta, I look at the two-point correlation function, the expectation of this jth coordinate at time t and at time s, and I average over all the coordinates. This is exactly this correlation function. This statement follows directly from this DMFT approximation that we had earlier, because from the Wasserstein 2 kind of conversions we had earlier. And the statement that doesn't immediately follow is a similar interpretation of response. So the response function that appears in this DMFT limit it represents the following thing. For each individual coordinate of theta, I make a perturbation to that coordinate of theta, and then I measure the response in that same coordinate sometime later. So I perturb that coordinate at time s, I measure the self-response of that coordinate at time t, and if I average this across coordinates, then the limit of this is given by this DMFT response curve. Right, so the statement of the correlation functions is direct. The statement of these response functions, what the proof needs to formalize or do is to essentially analyze the single particle dynamics, right? So we need to understand the dynamics of a single particle, perturbing a little bit the drift of that particle, and understand how this responds at a later time, and we do this using a sort of V1 out or cut-out D kind of argument for this response. I can maybe make one high-level point or one observation, which is that I can consider this kind of adaptive dynamics, but I can also consider dynamics where I don't adapt alpha. So I replace this adaptive process alpha by just the version of the dynamics where alpha is this deterministic process as described by the DMFT limit. And the result would be the same, that there's a DMFT approximation of the system, and the response would still be the same average response of that process. But the difference is that in that non-adaptive process, just by definition, if I perturb a coordinate of theta, alpha doesn't change. That's fixed and deterministic. Whereas in our adaptive process, if I perturb a coordinate of theta, that perturbation propagates through this alpha in some way, and that then propagates back to theta. But what I'm saying is that asymptotically in the large system limit, these two things are the same. So in other words, in the kind of process that we're considering, if I make a perturbation of theta, actually there is not really a propagation of that through this averaged alpha variable.
Do you have the convergence rate?
No. And I don't. For this, I don't think I've seen a convergence rate for this kind of thing. Actually, it's a good question. Right, and then so these are for the correlation response on the theta side, and then these other variables eta that represented x theta. There's a similar kind of statement, and the coordinate observables on that side would be the coordinates of the residual x theta minus y. Right? Okay, so given this interpretation of the correlation response, maybe the next thing that I want to explain is an analysis of these DMFT equations, for now, not in an adaptive setting, but in a fixed setting. So if I just don't vary alpha and I fix the prior in a very classical longitudinal dynamics for something like the posterior, I want to give an analysis of the DMFT equations and sort of see, try to make sense of what these equations should converge to in the long time limit or something. Okay. And so what I'm going to do is to motivate a set of assumptions about these correlation and response kernels that we expect should hold in settings where this Langevin dynamics is rapidly convergent. And to formalize a notion of rapidly convergent, let me look for illustration in a setting where, let's say, the posterior law that we're trying to sample from satisfies the Loxdorf. If you're not familiar with this notion, so we say that this posterior satisfies a Lox-Sobolev inequality if we have a bound on the KL divergence from any other distribution that's posterior in terms of this relative Fisher information quantity, and I'll spell out some implications of this in the slide. In the kind of linear model that we're looking at, it's sort of an open question under what conditions this Lox-Sobolev inequality actually holds. There are some known conditions. So for example, if the log prior is actually just globally concave, then this whole posterior is log concave and you have an outside. And then beyond this concave setting, if this log prior is only concave at infinity, and you have either sufficiently large noise or a sufficiently large dimension ratio n over d, this is what delta is represented, then we also know that a Lox-Sobolev inequality should hold. Let me not dwell on this too much. So what should we expect about the dynamics if this Lox-Sobolev inequality holds? So the first property that we know is that if I look at the infinitesimal generator of these dynamics, it's going to have a spectral gap. This is a point for inequality or spectral gap. And the second thing is that we should have a dimension-free contraction in the KL divergence converging to this equilibrium measure. And what this dimension-free convergence will imply is that, for example, if I look at this two-point correlation function for two large times S and T, large but dimension independent, then for large enough S and T, this two-point correlation function should look like as if I had initialized from the equilibrium measure. And if I initialize this from the equilibrium measure, I can sort of decompose, these coordinate observables Ej in the spectral basis of the generator of this process, right? And so there's some, I can think about the spectral decomposition of my generator and then kind of project Ej on the spectral basis and think about the behavior of the dynamics in this kind of way. And if we do a little bit more work, we can make similar statements about the response function. So if I look at the response function at two large times, I claim from this sort of explicit semigroup representation response function, you can check that for large enough times TNS, this behaves as if you're initializing from the equilibrium measure. And then if you initialize at the equilibrium measure, then because of the fluctuation dissipation theorem, this would be equal to the negative time derivative of the correlation function. So we have these kinds of properties that we expect to hold under this kind of slight condition. And this is going to motivate this definition that I'm going to call an approximate time translation invariant property of this DMFT system. So if I consider this DMFT system that describes the large system limit of these dynamics, we'll call this system approximately time translation invariant if there's some time translation invariant limit of the correlation function and some time translation invariant limit of the response function, such that as S and T go to infinity, my correlation response functions are well approximated by these limits in some sense. And furthermore, I expect a particular form of these limits. So if I look at what the correlation function should be, I expect that it's going to look like a constant plus an integration with respect to some limiting measure of an exponential decay. And this limiting measure, if I go back a slide, is exactly representing the high dimensional limit of when I averaged over these coordinate observables or projection onto this exponential. When I take n goes to infinity, the distribution of that over the eigenvalues of my generator is exactly this limiting measure. So this iota here is something positive, and this exactly represents the spectral gap, the generator, and this constant is arising from the projection just onto the space of constant functions. So we expect a very particular quantitative form for what this correlation function should look like in the time translation invariant limit. And then because of this fluctuation dissipation relation between the correlation response, we expect that the response is the time derivative. So if the DMFT system satisfies these kinds of properties and similar properties hold on the eta side, we call the system approximately time translation invariant. And based on what I was saying, you can check this that a sufficient condition for this, but probably not necessary. A sufficient condition for these properties to hold is that the posterior law satisfies laws. So under LSI, we can prove that these properties indeed hold for this limited system. Okay. So the theorem I want to explain is then this. So if these properties hold for the DMFT equations, then can I understand what the long time behavior of this process should be? And I claim that the answer is yes. So what should we expect? We should expect that this process will converge to the posterior distribution that I'm sampling from, right? And there's some understanding of, in the limit of large dimensions, what the posterior distribution should look like. So if I again fix the prior for a moment, I look at the marginal log likelihood with a negative sign, this is what I'm going to call free energy. And I look also at two mean squared error quantities. So one is if I look at the posterior mean and its average squared error for the true parameter theta star. And the second is a coordinate-wise average of the posterior variance. Then in the asymptotic limit, we have a prediction in some settings for what these things should behave like. So if my true prior distribution for the coordinates is G star, and G star is not necessarily the same as G, then in certain settings, we expect that this free energy and these two mean squared errors will have asymptotic limits that can be described in a very simple way based on a scalar channel, kind of Gaussian scalar channel. So in the scalar channel model, I just draw a single theta star from this true prior. I observe it with some Gaussian noise, and then I do posterior inference of that theta under potentially a different prior. This is the prior that I'm assuming in the dynamics, with also potentially different level of Gaussian noise. And the prediction is that in certain settings, this should be, so this kind of simple scalar description should characterize the limit of the free energy and mean squared errors, where these parameters omega and omega star describing the noise, and these two limits of the mean squared errors, they're going to satisfy a system of scalar fixed point equations, and I'll show you the equations. So this kind of theory is most well developed in a setting where this assumed prior G is the same as the true prior G star. In that setting, basically this whole story is by now well established and known. So the heuristic calculations of this and the first heuristic results were due to Tanaka. And then over the past, 5 to 10 years, there's been a long line of works by Jean Barbier and co-authors in particular that formalized mathematically this kind of statement that this is indeed behavior of the posterior law. We're interested in settings where this G is not the same as the true prior, because the way we want to eventually apply this is that, this free energy, if I consider the G that's for a particular prior parameter, then this limiting free energy is exactly the limiting log likelihood evaluated at that parameter. So we're going to want to look at what this free energy looks like as a function of this parameter, which means that I need to consider hypothesized priors that are not necessarily true. So in this setting, my understanding of the literature is that the heuristic calculation perhaps was first done by Gore and Verdu, who produced these kinds of replica predictions. There was a generalization of this due to Kawashima, and there's not much rigorously that has been written down about this. So in particular, I don't know of a rigorous statement of this result in the specified setting. There is a closely related result that was done by Barbier, Chen, and Pacheco and Saenz that looked at a slightly different setting of this, where the likelihood was misspecified instead of prior and everything was locked. So this is sort of, so when I say that, we expect this to be the picture, it's sort of at a heuristic level. Yes.
Prior case, then the replica signature is also not immediate.
Yes, right. So if your prior is correctly specified, this picture is always correct. It's always replica symmetric. If your prior is misspecified, it might not be. So it depends on what is the true prior and what is your assumed prior. And there are settings where this is correct and settings where this is not the correct picture, and you have replica symmetry breaking for the posterior. The theorem I want to state is that this replica symmetric picture is correct under this approximate time translation invariance property. So what we're able to prove is the following, that if this DMFT system is approximately time translation invariant, it satisfies these conditions I stated earlier, then we can read off what the prediction should be for the mean squared errors, first of all, just from this DMFT and the dynamics. And those quantities that we read off do indeed satisfy the system of replica symmetric fixed equations that we would expect. So these are the four equations that have been shown on the previous slide. Furthermore, if I look at the law, so I have this DMFT process theta t. If I look at the law of theta t or the joint law of theta star, it's going to converge to a bivariate law that's described by the scalar channel. So this bivariate law is I sample theta star from this true prior G star. I sample y as a noisy observation of that. And then I sample theta from a posterior defined by a different prior. And whatever is the joint law of theta star theta, this is exactly the limit of the joint law of the DMFT process of theta star. I think I am trying to be overly ambitious, so maybe I skip the proof idea for this. So there is a proof idea here. Perhaps I don't try to explain. I can explain this, which is one corollary of this result is that this implies a proof of the replica symmetric limit of the free energy and the mean squared errors in this setting where I have posterior LSI. So if I have a fixed prior and I know that the posterior distribution satisfies a Max-Sobolev inequality, then we can kind of push that previous result to the long-term limit and show that the limiting free energy and the limiting mean squared errors and also the limiting empirical joint law of coordinates of a posterior sample with the ground truth theta star do in fact converge to these symmetric quantities. And what this is establishing is I guess it's a different kind of a proof of this result. So in recent years, there's a large body of literature that proves these sorts of results. A lot of the techniques for proving these results are based on interpolation kinds of methods that were developed by Guerra and Brand. And our analysis is providing a different sort of dynamical proof of these results, that we're obtaining these results instead from an analysis of a longitudinal process that's converging to this posterior and reading off these fixed points from this limit longitudinal process. Okay, the last thing I want to say is going back to the original motivation, this empirical Bayes kind of dynamics. Let me state the result here, and then I'll show you some pictures and examples, and then I'll conclude. So our final result about this adaptive dynamics is the following. Suppose that there is some bounded domain O for which I know that this parameter alpha that I'm learning, whatever it is, remains confined to O. Usually we need some external argument to show that this alpha is confined to O. This is example dependent. If there is such a bounded domain O, and furthermore, my posterior laws for all of the parameters alpha in this domain satisfy uniformly Max-Sobolev inequality, then we have the following statement. So let me denote by now thinking about this as parameterized by alpha, the limit of the free energy, FRS, and then the limit joint law of this my posterior sample in the ground truth, theta star. The result is the following, that in the long time limit, this DMFT variable alpha t will converge to some fixed point, and this fixed point will be a critical point of this asymptotic limit for the free energy. So you should think about this F alpha as the limit value of the marginal log likelihood for each parameter alpha. We can check that it's differentiable in this limit. And if you look at the set of critical points, then the process will converge to one of these critical points. So one implication of this, so I'm not making a claim that there's a unique critical point or anything like this, but the set of critical points is dimension independent. It's just some asymptotic limiting object. And then consequently, if I fixed U any epsilon for some large but dimension-free time, my estimated parameter will be close to this critical point, and the joint empirical law of coordinates of my longitudinal sample in the ground truth will be close to this sort of replica prediction that the joint law should be between the sample from the posterior and the truth. Okay. And let me just conclude with a few examples of concrete examples. Suppose that the model that I have is just it's a scalar location model. I have some function f that defines a potential, smooth, and suppose that f is actually strongly convex, and an alpha is parameterizing the location this prior. This is a very simple setting. In this setting, we can say a lot. One thing is that we can actually check that the posterior LSI holds because this is a log cave problem. And then we can also check that there's a unique critical point of the replica landscape, of the free energy landscape. So in particular, if my true prior corresponds to some true parameter, the critical point has to be the true parameter. And so what we're guaranteeing is that we are correctly learning this true parameter. And the samples that we're drawing are going to be close to samples from the posterior log. This is a very simple setting. Outside of the simple setting, let me just present some examples where we have a little bit of theoretical analysis and then some numerics. So suppose that my prior is a Gaussian mixture model, where alpha is parameterizing the means of the mixture components, and then I'm fixing the mixture weights and also the mixture variances. In this setting, what we can say analytically is that in a regime where I have large enough noise and a large enough dimension ratio n over d, I can check that this Lox-Sobolev inequality is going to hold all the bounded domains. And I can also understand the free energy landscape. So the landscape of this marginal log likelihood as a function of alpha. The critical points of that free energy will be in one-to-one correspondence with critical points of just a univariate Gaussian mixture model where I have some slightly elevated noise variances. And the landscape of this kind of Gaussian mixture model is something that's well understood. In general, it might have more than one critical point. And so what our theory says is that this dynamics of alpha is going to converge to some critical point. I don't know which one, but whichever one it converges to is just deterministically determined by the initial conditions, right? Because this whole thing is a deterministic process. So I'll show you some pictures. So you can ask what happens for smaller values of delta, things like this. And so when I'm plotting here, just in a simple example where I have only two mixture components, so I have two unknown mixture means, alpha 1, alpha 2, we solve these fixed point equations and compute numerically what the free energy landscape should look like. So there's a numerical computation of the replica symmetric limit for free energy. And what you're seeing is a heat map of this. And what you see is that, okay, so the true parameters we're taking as -1, 1, and that's always this point here. So that's always the global minimizer of this free energy. And then it seems that for all possible values of delta, which is n over d, there is a second local minimizer of the free energy. The second local minimizer, so here I'm taking the variances of the two components to be slightly different from each other. And the second local minimizer is roughly close to a configuration where the two means are reversed. Or I think that the component with mean close to -1 has variance a quarter instead of 1, and vice versa, right? And one observation that we see is that as the dimension ratio n over d is smaller and smaller, the value of the free energy at these two minimizers start to approach each other. So statistically, it becomes harder and harder to distinguish which of the true configurations it is. And then if you compute the mean squared error of my Langevin sample, so we can read off from this theory of prediction for what that mean squared error should be. And the predictions are what I'm showing as these dashed curves here. So in each of these examples, we're running the dynamic starting from the one initialization that's close to the true minimizer and one initialization that's close to this local minimizer. And depending on which one it converges to, you get a different value. So this blue curve should be close to, if I were to pick correctly the true prior, if I know the true prior, what this error should be. And the green curve is if I estimate the prior by this other various local test. Okay, one last example. If I consider a Gaussian mixture model where instead of parameterizing the means, I fix both the means and the variances, and I just parameterize it by the mixture weights. So alpha here is representing the weights of this mixture component. I can also do some theoretical analysis and some numerical analysis of the sample. So again, if sigma squared and this dimension ratio delta are large enough, we can check that the posterior LSI will hold actually uniformly over these mixture weights. We can also check that in this case, there's a unique critical point of the free energy landscape. This is sort of for the same reason as before, that there's a one-to-one correspondence between critical points of this and a critical point of some scalar Gaussian mixture model. But here, if we parameterize by the weights, then there's a unique critical univariate Gaussian mixture. Right? So we can read off this uniqueness. And what this means is that for large sigma squared and large delta, we would be correctly estimating the true weights alpha. When we do numerics of this, it seems like there's a unique critical point even for smaller values of sigma squared and delta. We are not able to prove this so far. But this is just a numerical illustration. Again, I'm considering just 3 mixture components with 3 weights that sum to 1, so they're simplex. And then there is a true mixture component alpha star, which is shown in this red star. And what you're seeing are trajectories of the dynamics for 3 different initializations. The green one, we're also initializing the Langevin sample theta to be the ground truth. And the other 2 we're initializing that to be some IID. And what you're seeing is that for large values of the dimension ratio n over d, the process seems to converge successfully and during these correct leads. There seems to be a threshold of delta at which this process stops converging to the correct thing. Now, it's not because there's a spurious local minimizer of the free energy landscape and the settings. We think what this is due to is a slow mixing of much that's stuck in some metastable kind of state. It's a setting where this, for example, this Lux overlap condition is not. So right before this kind of setting, in this picture that I'm plotting here is again the mean squared error of iterates plus iterations. And again, you can kind of see that the prediction for the mean squared error also converges to our theoretical prediction. Okay, let me conclude. So what I've said is that in a Bayesian linear model, we can try to learn an unknown prior parameter by using this adaptive kind of empirical Bayes procedure. Focusing on just a setting of IID regression design, there is a sort of single chain propagation chaos kind of result that should describe the limit of the empirical distribution of coordinates of the Langevin sample and we learn prior parameter. And this limit is described by this dynamical mean field theory. We postulated a particular assumption or condition on this DMFT system, which is that it satisfies these approximate time transition invariance properties. It's an assumption that we can check, for example, if the posterior law satisfies Lux overlap condition. And under this assumption, we can show that this DMFT process will converge to an equilibrium state that's characterized by some simple scalar Gaussian channel model. So it's a replica symmetric kind of limit. And if this posterior LSI holds uniformly over the trajectory of this alpha parameter, then we can establish dimension-free convergence of these dynamics to a fixed point of this limiting energy. Okay, that's all I wanted to say. Sorry for keeping you guys a little bit, but thanks. These are the references. I apologize a little bit that the papers are not yet posted, but we'll be able to post it in a week or 2. So thank you.
Question for the speaker?
So I thought it was between points 3 and 4. So I thought point 3 was for the non-adaptive dynamics, but then from this you're able to use point 4, which is probably adaptive dynamics.
Yeah, yes, I didn't explain how you go from one to the other. You're right that in point 3, the analysis was all for the non-adaptive dynamics. The analysis of point 4 is some hybrid of this mean field kind of analysis and the usual sort of the up and down function analysis. Because the proof in point 4 is using this viewpoint that this process is carrying out a gradient flow, a Wasserstein kind of gradient flow on the Gibbs variational function. So you have the Gibbs variational representation of free energy that's providing the up and down function for these dynamics. And because you have this up and down function, we can kind of argue that it should converge, and the process can't oscillate or something. So it should converge to some fixed point. And then the fact that this fixed point has to be characterized by this kind of replica symmetric theory is using our results.
Do you think there's some kind of similar assumption that you can make on the posterior distribution, which will be the sort of capture the behavior of the non-replica symmetric vision?
Yeah, no, that's a good question. So we haven't, I don't have any understanding right now of the non-replica symmetric regime. So there's something that's new. Okay, so one of my co-authors, actually Justin, has a nice paper recently where they analyzed the free energy landscape of not this linear regression model, but some spiked matrix model. So we just have some noise plus a rank 1 spiked matrix, and they characterize the full limiting free energy in that problem in both the replica symmetric and the RSB regimes. In general, it's given by some much more involved variational characterization of like a Parisi type. And it's not well understood at what points that reduces to something that's replica symmetric versus at what points the solution of that variational problem is in fact full RSB. And then from this kind of dynamical viewpoint, I don't think we have the tools or techniques right now to Andre.
Thank you. So for the first example of the low concave fire, is it possible to analyze the dynamics more explicitly? For example, like finite entity.
Yeah, yeah, so, right. Yeah, that's a good question. For the log concave prior action, and the reason why we know there's a single unique fixed point is there's actually a direct argument for finite ND that's just the marginal log likelihood. It's from the convex of this is convex in alpha. And because you have the strong convex in alpha, and you have probability to and now, so in that setting, actually, you can get these results, I think, without IIT calculating something. So you can just do the analysis with finite ND using standard tools and it will derive at the same time.
You mentioned early on in the slides talking about like the gradient of the alpha being potentially intractable because
Yes.
we can't compute those expectations.
Yes.
But if we're assuming this LSI inequality, shouldn't those expectations now be pretty easily computed via like, your favorite MCMC algorithm?
Yeah, I guess that's what I'm sort of saying with this.
Yeah, so I wonder like, could I not just run longevity on the alpha to begin with? And like, what's the contrast between this method and just doing that? I
Okay,
guess.
what is the alternative that you can do?
Like just run Longevin diffusion on the posterior distribution of alpha. And as you need the score, compute it via its own little sub MCMC method. And then you get alphas drawn from the true posterior.
Oh, so, okay, alpha, I guess here, I'm not putting a Bayesian prior on alpha, so we're just trying to do some deterministic gradient descent kind of thing on alpha. But I can, I think that this method is not something that's like crazy, right? I think that maybe the approach you're suggesting is the standard thing that people do, which is I fix my alpha, I do some posterior sampling, maybe I wait till that posterior chain equilibrates, and then I compute, I compute the gradients at alpha based on those posterior samples. And what you're pointing out is that because everything satisfies LSI, that posterior sampling should rapidly equilibrate, so it's not really intractable.
Yeah, I just wonder, like, is the benefit here, like, is it somehow faster computationally? Is it more accurate? Like,
Yeah,
I guess, like,
I'm not
in this
making.
LSI system, what's the argument for this over other methods that might also just work?
Yeah, sure. I'm not making a theoretical claim that this is going to be faster mixing or anything like this. I think it's just very natural to do. I think the way people implement these things in practice is probably not to wait till the chain equilibrates. Like, I think the difference is if I want to approximate some posterior expectation, do I actually need to equilibrate the whole chain and then use that, or can I just run a few steps of the chain and immediately update out? I guess what I'm saying is that it's very natural. It's an implementation hack even to just do that, right? I just draw a few samples and I take a small step. I think once you start thinking about these kinds of hacks, it's kind of interesting. But I'm not claiming that these hacks are essential. It's going to improve.
No more questions? I think our speaker.
Thank you guys.
Thank you. We're gonna set up the time.